Okay guys, this is my second video here on the channel. I was really pleased with the feedback I got on the first video, which was a review of the uh, shit audio Wally 2 tube hybrid amplifier. Hopefully the video and audio quality should be much better because I was using a point and shoot camera for that first one, not a proper camcorder. So now I have a Sony AX100 and proper audio setup here. So hopefully that should be a lot better than the first video. So today our topic is going to be something really sort of technical in nature, but I'm going to try to make it as easy to follow, and it's going to be digital filtering. So originally, this is going to be I guess a three-part series where the first video is going to be about digital filtering. The second video is going to be about what I originally started this series to be the series to be about, which was going to be DACs, digital to analog converters, and if needed, a third part which will explain a specific type of DAC, the Delta Sigma DAC architecture. So if I can fit it in, I'll do it in the second video, but the second video is going to be all about DAC. So we're going to get to some of you might have heard or own the multi-bit DACs, such as the ones from Shit Audio, the Gongnir, or the Yggdrasil, or the now they just released, I believe, a Modi multi-bit. So they have and Bitfrost. So they have multi-bit DACs, and so we're going to be talking about I guess what multi-bit it really is, but we're also going to be talking about uh, the DAC architecture in general. So when I say DACs, I'm going to be talking about a bunch of DACs before I get to the traditional audio DACs. So we're going to be talking about like R2R, binary weighted, sort of the traditional real in quote DACs that use passive components, but are the real bit rate. So when you have a 20-bit DAC, you get 20 actual bits, and so on and so forth. So that's going to be for the second video. But really, before we talk about DACs, uh, an understanding of digital filtering is needed. So what is digital filtering? Well, digital filtering is the precursor to pretty much any DAC on the market today. Now, you can get a DAC on the market that, well, when you buy a DAC on the market or a DAC chip, many of them will have a lot of these filters pre-built, a lot of the handmade sort of famous audio ones. They're all Delta Sigma in that case, and they're all based on these filters that are generally already there for you, if not already fully enabled and designed. But what we're going to talk about is digital filtering, and we're going to be talking about it not necessarily uniquely to audio, although I'm going to have a focus towards audio. So the implementations, I'm not going to cover everything because I don't have 5 hours, but I'm going to talk about specific audio filters that you would use towards audio. But again, a lot of this is just general knowledge, so it could be used for filtering in many scenarios. And remember, DACs are not only for audio; DACs are for any digital to analog converter. So we can use them for MRI, for other medical applications, for analysis of many different types of signals and frequencies. I mean, audio is just the tip of the iceberg. It's low frequency, but we're gonna talk about filtering in a very general way. Although I'm going to have examples that are based on the audio spectrum, and when I do my examples, I'm going to be putting them in the audio frequency range. So I'll try to keep a mix of general and also specific to audio, but I'm trying to cover a lot in this video. So Hopefully you guys stay with me because understanding digital filtering and some of the nuances in the digital filtering process really gives you a good understanding of the entire audio spectrum, if you want to say, or even the entire frequency time correlation. And it gives you an idea of a lot. So filters are used, digital filters are used in DACs, and they're used before the DAC. So before the actual digital to analog conversion, we have a filter. And so all the top DACs you see, all the high end DACs, they all have digital filters, and that's actually what I would say makes at least 70 to 75%, if not more, of the performance, and gives the DAC the sound structure and the hologram that it has. So, when someone says, I like this specific DAC or I like that DAC, if they're high end DACs, they're going to be really influenced by the digital filters, and that's really where a lot of the innovation is coming. It's not really the DAC, because the DAC is just doing in digital to analog conversion, so it's not that special. At the end of the day, I mean, there are benefits to using better DAC chips, as we'll talk about in the next video, but moreover, the filters are really important. And so, I pull a lot of the slides, if you want to call them that, from this really, really great 40 to 50 page book, a mini book from Analog Devices, which are one of the leading chip manufacturers. They make a ton of DACs and a ton of ADCs and a ton of other things. So if you are interested, I'm going to leave all the sources for everything I use in the description, but the Analog Devices mini book is definitely a great resource because it's not too technical and covers a lot. Now I'm not covering everything in there because of course I don't have that much time to do so, but if you are interested in digital filter design, it's a great place to start, and there's a lot more information in there that definitely will come in handy. But I do pick quite a few slides from there. Now, let's look at the first thing. So, what is a digital filter? How does it compare to an analog filter? Well, remember, when we're working with digital data, right, we're working with binary data or numerical data. We're working with actual numbers. So that gives us the power to modulate these numbers, similar to how you would modulate or similar to how you would not have an issue, rather copying and pasting, say, a WAV file, which you downloaded from a website. And you can now copy that and you can give that to your friend, you can email that, you can do whatever. The fidelity of that WAV file is not going to be lost. So you're not going to suddenly crop that WAV file unless you purposely do something to it. So you really have perfect fidelity because you have digital audio, in the sense that reproduction is not an issue. So that is one issue with vinyl, with analog, with reproduction or fidelity. As you make copies or as it ages, you have to be careful because the analog data is right on the vinyl, and if you scratch it, you're going to interfere, you're going to destroy part of the data potentially, and so you're going to cause problems. And furthermore, digital filters give you a lot more accuracy because you're able to actually work with the digital data. So if you're comparing it with analog filters directly and you're already going to be working with digital data, then digital filters are obviously the way to go when you're talking about a pre-stage for a DAC, which is what I'm going to be focusing on. But of course, you could use them for other things as well. Now, so with digital filters, you get the typical benefits that you would assume come from modulating digital data. So we get high accuracy, as I mentioned, a linear phase, which I will talk about a little bit later because we're going to be talking about FIR filters. That's really the heart of this video. Uh, we have no component drift. Really, that's a big deal because analog filters use passive components like your capacitors, your resistors, whatnot. And so, if those components have issues, well, then you're going to have issues with your filter. Now, DAC chips themselves have that, especially R2R DACs and other things because they're using resistors. And that is a topic, again, we'll cover in the next video, but that is not nearly as much of an issue due to the laser etching and the high quality, high matching we can get with resistors these days, especially when there's not that many of them. So we're not talking about hundreds and hundreds of resistors. We're just talking about, like under 100 resistors for the top DACs. So we have no drift with digital filters generally. Now, designing them is easy in the sense that you have software, and most DSP chip manufacturers or even FPGA manufacturers offer some type of software that you can work with. So it's like designing, programming onto this specific chip. Many of these DSP chips are enhanced with algorithms that make it easier for you to do digital filter design. In fact, digital filter design, if you're just trying to do it out of the book, just tools like MATLAB and many other tools that you can download for free or for very low cost will give you the entire code and all your filter information. So it's relatively easy. Now, if you want to design your own digital filter from scratch or combine different windows or look into some more advanced techniques, that is where the real fun comes, I guess, and that's where the real challenge comes because you have to do it yourself. But that's really what differentiates sound signatures from DACs. The filters really make a difference, but they're easier to design because you don't have to sit there and actually use a breadboard and or solder actual components together and then test them with the oscilloscope or spectrum analyzer and do all these actual hardware tests. I mean, take out it's not terribly hard to use a breadboard, but to build something like that and then you have to put it in your product and see how it goes, it can be sort of a pain to do because you don't know how it'll turn out once it goes off the breadboard. So working with actual hardware is not as easy as just working with software where you can just backspace delete, load on. I mean, you have almost limitless opportunities. However, unlike analog filters, you need some type of relatively high power DAC, but more importantly, you need a high performance DSP, or a lot of people, manufacturers are using FPGAs these days. So you need some type of chip that's going to be the beef of the algorithms that you're going to be performing in your filters. And remember, the filters are really the heart of the system here. So the chip that's doing the DSP, whether it's an FPGA or a DSP chip, they're going to be usually pretty beefy chips. I mean, they're generally pretty powerful, and they're definitely more powerful than the actual DAC. I mean, the DAC is not doing a whole lot once the filter is really doing a lot of the work. So the DAC is going to take the data from the filter generally, and it's just going to be referenced to a positive and negative voltage, and it's going to do its conversion and bounce between those voltages. Now, we'll get into a whole lot more detail than that in the next video about DACs, but generally the filter chips are really more akin to like mini CPUs that are specialized for the task, and they are pretty powerful, and that's what's allowing such unique filters to come to existence is the more high performance DAC and DSP chips that exist today. So we're done with that one. So let us look at And I do everything printed out, like old-fashioned way, just in case I have to write on anything. So bear with me here. So let's look at our types of digital filters. So we have the moving average, which we're not going to really talk about very much. It's really actually a very simple filter. It's just as you would assume by the name, a moving average. So it's the average of the input, and the coefficients are generally the same. And it's why it's called a moving average is because you're sort of moving in this circular pattern, and but you're cutting out one sample, so you're utilizing this algorithm where you utilize the old samples to get the new information, and it's a moving average, so it really just calculates the average in real time as you move along. What we're really going to be focused on is the second bullet here, the finite impulse response filters. Really going to be focused on that. That's what the heart of this video is. So the finite impulse response filters are linear phase generally. I mean, you can screw that up, but generally the linear phase, and that's one of the main characteristics of finite impulse response is the linear phase. They're easy to design in quotes, as in you can easily design them if you want to, and you're not really designing them. I mean, you can use tools that are available to generate basically all you need. They're computationally intensive, as we'll see, because you need to actually do multiplication and addition for each individual step or tap in the filter. So we'll get into that. And so IIR filters we're not going to talk about in this video. They're infinite impulse response filters. They're of course based on classical analog filters where you're working with continuous domain data. They are based on a lot of feedback. They utilize a lot of feedback, and so they can go on. The impulse can go on forever. A lot of crossover networks will utilize infinite impulse response filters, and indeed a lot of our good in fact the one we're going to be example that we're going to be looking at today with the FIR filter, it's actually sort of not derived, but very heavily borrowed from sort of the idea of an IIR filter, because we want to mimic that infinite nature, but we can't. But so we want to do imitate it, and oftentimes we can utilize some of these IIR filters and look at their sort of FIR equivalent, if you want to call it. Now, lattice and adaptive filters we're not going to talk about at all. They're more advanced. And if you're interested, I'll make another video after the DAX series is over about those, and especially about some cool ways of interpolating, like Lagrange polynomials, the FARO method, and so variable delay filters, which are a little bit more advanced type, but they offer some really good benefits. They're maximally flat, which we call at DC, so they're very flat, which at low frequencies. They do have their issues, but if done right, they perform very well, and they provide a closed form solution. They're sort of newer, if you want to call it that. They're polynomial based. I mean, it's a mode of interpolation. We'll talk about interpolation in a little bit. So that is just a quick overview of digital types of digital filters. So let us look at the processing requirements for real-time digital filtering. So this is a general processing requirement for any real-time digital filter. So you have your bandwidth, right? Let's assume it's 20 hertz to 20 kilohertz, your audio frequency bandwidth, the standard accepted, well-known audio frequency 20 to 20. Uh, and so let's assume that's what we call FA. Of course, we know by Nyquist. I'm not going to go into Nyquist in great detail in this video. If you want to pause and just Google Nyquist Shannon sampling theorem, if you want to know some of the mathematics and the proof behind it, feel free to do so. It'll definitely help. But generally, most people know that the sampling frequency has to be, of course, 2 times the bandwidth of the signal that you want. Otherwise, you're going to get aliasing. So that's, of course, what we require. Now, our sampling period is simply, again, by Nyquist, 1 over the sampling frequency. And so that is our sampling period. And our computational time for a filter, now this is important, plus some overhead, which we always do for good filters. You always want to have overhead. It needs to be less than the sampling period. So if you want to think about it like this, the filter needs to compute everything it needs in the sampling period to all the samples in that sampling period before it can send it to the DAC or send it to whatever it's aiming to do. But it needs to do that within the sampling period, because the next sampling period comes, there's going to be a whole new buffered amount of data. So remember, we're getting digital data here from some source like your computer or through USB. It's being clocked, and again, this is now going into DAX a little bit. It's going to get clocked, it's going to get buffered, and there's schemes to do that, but it's going to get essentially blocked in, and then it's going to be sent to the filter, and then the filter is going to have to do its tasks, and all of the computations before the next buffered amount of data comes in. So you need to compute this, and you can compute this when you know your chip, when you know the DSP chip you're using or the FPGA. You can actually compute it by utilizing exact measurements to see how long it takes to do one cycle, and then and go from there. So and some of these chips even have tools right out of the box to do that. So we use this term multiplication accumulates, MACs. It just means multiplication and addition. So each time you hear MAC, one MAC means one multiplication and one addition. So generally the speed of a DSP depends on how well it can do MACs. And then we have other benefits like the circular buffering and zero overhead looping, which I won't go into in this video, but they are just some exploits, if you want to call mathematically, that DSP chips will take advantage of because they know that they're being used for digital filtering, and so they can use it similar to how an ASIC chip or a specific hardware chip will have firmware that's designed to enhance your task at the hardware level. So really what's to take from here is that your computational time needs to be less than the sampling period. Alright, so now we get to some important pre-topics, I guess, or topics that'll lead us up to the filter design that we're really going to talk about. And this is almost as important to understanding filters as just designing filters actually is. So this duality of time and frequency, so this is really a beautiful thing. Once you understand it, it really will give you an idea of how time and frequency domains are actually very interrelated. Now, I'm not going to go into FFT DFTs. So an FFT is just the fast Fourier transform. Many of you, I'm sure, have heard of that. And the algorithm to compute that efficiently is the FFT is the algorithm to compute that efficiently. I'm sorry. The DFT, the discrete Fourier transform, is the same as the FFT. So you'll often hear me saying discrete Fourier transform because these days people use them interchangeably, but really they're not the same. One is an algorithm. The FFT is an efficient algorithm that's widespread and mainly used, but it's the same exact thing as the DFT, as in the computation results are the same as the DFT. It's an equivalent thing. It's just it's an algorithm, a fast algorithm. So really, the correct term is DFT, the discrete Fourier transform. But we look at this figure here, and we're really going to be focused on the second part here. So we have the frequency domain on the right and the time domain on the left. And so you can see here, specifically in the middle, we have what we call a realistic frequency representation transfer function, capital H of k. And then we have a realistic impulse response function in the time domain, lowercase h m. And to get from h of k to h of m, we're going to simply take the discrete Fourier transform of the transfer function. So if I'm not going to go into the formula for the discrete Fourier transform or compute it, because there's so many videos out there about it, but we're going to be doing that to get to this, from here to here. So I want to take a minute here and pause. So let's try to understand these images, because they're very important. So you have your frequency domain here, and again, the frequency domain is going to show the components of the frequency. So I have this other image, and I apologize for the quality here, that is a three-dimensional sort of graph of a Fourier series, and you can see the frequency domain over here. So we have a frequency domain over here. We have 6 sine waves that make up this signal, and then we can see in the frequency domain the magnitude. Again, the x-axis is the frequency, and the magnitude here. So in the frequency domain, we're seeing how much each of these waves makes up the signal. We're seeing the frequency component separated in the x-axis, and the y-axis is something like decibels. So when we talk about decibels, right, when we talk about something like the decibel, right, we're talking about a ratio. So it's a ratio, and that means we have endless units. And what I mean by that is we can use this basically for any two power derivations. We're not limited by, say, inches or a unit that is derived from a specific or meant for a specific task. So we are able to use a ratio, and so we're able to compare power levels between many different things. That's why decibels are used for many different things. It's a relative measurement, right? So you can have decibels here on the y-axis, or in much theory, we're just going to have it normalized. So we're just going to have it from 0 to 1, and even our frequencies will be normalized. So you can have your frequencies in hertz, like you traditionally see it, hertz to kilohertz and above, or you could have it in normalized frequency, which will be going in radians. So again, trigonometry, if you remember your unit circle there, you get your radians. So generally it's from 0 to 1, and it's called a normalized frequency on the x-axis. So again, this is our signal, this is our frequency components of that signal, and then these are sort of a 3D slice showing the actual waves that are made up in the signal, and the frequency Fourier series representation here. This is the frequency domain. Now, what's important here is that this is again a realistic filter, specifically a low pass filter. So here we have frequency components that are spurs. Of course, this is 0 or DC, and then we're going up in frequency. This is a low pass filter. So when you multiply this this graph of in the frequency domain by its transfer function in the frequency domain multiplication, you're just going to get, in this case, this first one, because these three don't actually fit in this low pass filter. Now this is a low pass filter because it's one or flat at all the frequencies that we want to accept, starting at 0, and then it has a cut off. Now ideally, in an ideal setting, in a perfect world, which we can never have, our low pass filter would look like this. So I'm going to just draw the ideal low pass filter, which is a rectangular function. However, that's not possible in real life, and so we get really, these days, really steep filters because of all the powerful DSP chips, and we'll look at that in a second. So this is sort of an attenuation curve, right? So it's not perfect. Again, a perfect low pass filter would accept all the frequencies that you want up to a certain frequency. So up to some frequency, we call it FC, the cutoff frequency, say 20,000 hertz or 20 kilohertz, and then it would just cut all frequencies. So it would go from 0 to 20 kilohertz, and then it would just immediately brick wall and not allow anything else through. In real life, we can't do that, so we get pretty steep filters these days, and the steeper or the closer you get to this pure rectangular function, the better you get, the better filter you have in general. So you see here that we get a slight attenuation here, so it's not a perfect cutoff, but it's a pretty steep one, so it's not allowing any frequencies through, and then there's going to be the 3 dB and the 6 dB negative point, and this is going to be a pretty fast attenuation. I mean, generally you'll see in the example that in the end that the filter that we build will only have it will only have a 2.05 kilohertz. So I'm making it so steep that within 2 kilohertz you have 100 decibels below the frequency, so 100 dBm below the passband frequencies that you want. So that's a very steep attenuation from going just from 20 to 22.05 kilohertz. But we'll get into that in a minute. So you can see here when you multiply, you're applying this filter onto this, so you only get this because these three can't pass. Now, these are higher frequencies, so of course we call this a low pass filter because it allows the low frequencies to pass that we want up to a certain amount, and then it attenuates. And this is the transfer function in the frequency domain. Now what's important are these three topics, and actually before we get to the three golden topics, I'm going to take a deviation. So again, one last mention here before we get back to it. The DFT of this, the discrete Fourier transform of this frequency component transfer function, results in the impulse response, right, in the time domain. Now, what is the impulse response? So this is where we're going to do some mathematics. And so just going to put that in ahead, and we're going to get out some paper to do some calculations. So I'm going to try to keep this as basic as possible. Hopefully you guys follow along. Now I'm not going to go into too much DFT theory here. We're just going to actually talk about discrete sampling, because that's what we're talking about in this video. We're functioning with discrete data. So digital filtering doesn't have to be with discrete data, but it almost always is. So what we're gonna do here is try to derive the formula for the next slide, which is the general n-tap FIR filter response. That sounds kind of scary, but bear with me here, and hopefully this will make a little bit more sense. Now I'm doing this because I sort of want to show you how this formula is derived. I could just show you the formula and not give you any information about it whatsoever, but we're going to go ahead and derive it. Now this is not a complete full derivation. You can get into a lot more detail in this for each specific part, but again, I'm doing this balance between simplicity and theory and complexity. So let us go ahead and define the following. We have a signal x. We're just going to call it some signal. So we have some arbitrary signal x. Now x is just some discrete signal that we're going to be actually sampling, and so we want to represent xn. Now what is xn? Xn is, get that in the shot, xn is going to be a sequence of numbers. So it's going to be discrete, and what we're going to do is try to first derive a formula for xn, and then talk about some functions about this formula. So the first thing we need to introduce before we actually go into the formula is the concept of LTI systems. So LTI means linear time invariant. So it's a linear time invariant system. So what does that mean? Well, a linear time invariant system is one that is invariant time and linear. So linear simply means that we're able to essentially apply group operations to our functions. So this is really handy, and you'll see when we're done deriving this formula why it is, because it allows us to actually do things like just the basic algebraic method, that you would do. So the group operations like the commutative property or the additive property, just simple things like C times A times B equals B times A times C, or simple properties like that. Just the ones that you use in algebra you can use with linear systems. In general, it means that you have an input, let's just call that x of t 1, that leads to an output right, and then you're also going to have y sub 2t that's going to lead to output y sub 1t, which is going to lead to output y sub 2t. So it's saying that you have inputs leading to outputs in a linear fashion. You can apply group operations here. So you can apply group operations here to this, and by group operations I mean properties such as the commutative property, which is going to become in handy, the additive property, just your basic algebraic properties. So what is time invariant mean? Well, time invariant simply means that our system is not relying on time. And what this means is, so our real-time systems are generally time invariant because by nature. So time invariant means that first I'll write it theoretically. If we suppose we have two sampled signals or systems, we go x of t, y of t, and suppose we sample them now. We have so these are the sampling responses of x of t and y of t. Now let's take a time delay of t. So we have a t delay, time delay. A time invariant system states that the output of this will be equivalent to the input or the original time, the original representation, just delayed by some time. And this is a constant delay. And so this what this is saying is our system is not inherently variable with time. Time doesn't actually influence this system. We don't have to worry about time being an influence. If we input a signal 5 samples from now, so 5 samples in the future, or in the past I should say, the output of this system will just be simply the original output, or the regular characterized output with a delay of 5 samples in this case, or whatever the delay may be. So it's invariant in time. So all the filters that we're going to be talking about are LTI, all based on LTI systems, and the properties we're going to be using are based on LTI systems. There are nonlinear systems and non-time variant systems, so time variant systems where time does matter, but in the case of what we're doing, so real-time digital filtering, even more specific for the case of digital to analog converters, that is actually going to very rarely be a deviation from LTI. Although, if you don't do your, if you're designing from scratch and you're not doing your design correctly, you can make a filter or a system non-linear or time variant, and that messes up everything, and that makes all these properties that we're working with not valid. So let us go ahead and derive some of the formulas that I was mentioning. So so there's going to be a little bit math here. So again, we have our signal xn that we're trying to talk about. Now this is a sequence of discrete values, all right, and there's going to be a formula here that we discuss, and it so I'm gonna break it down sort of like this, even though this is not, I guess, the classical way of doing so. So let's break it down like this. The response of this at some point is x, and we're going to put this variable t, and you'll see in a second why. Actually, we'll call it k times now this you might have heard of is a delta operator, also known as a delta function, even though it's not really a function. However, in the discrete domain, which is what we're going to be talking about, we can describe this as a function. So a Dirac impulse is really a pulse. So the definition is it's zero everywhere, and then it's infinite at 0. So at the point 0, it's infinite. And so obviously that's not possible in real life. So we can approximate it, and in the digital or discrete domain, right, we have an approximation of this. So it's simply that so we call this the Dirac delta, or a function, and I put it in quotes because it's not really a function. It's a sort of a weak function. Mathematically speaking, it has a weak Lebesgue limit, but that's again out of the scope of this video. In the discrete domain, though, we have a nice approximation we can use, and it's simply that at any point except where this function is not equal to 0, it's going to be 0. When this function is 0, it's going to equal to 1. So we can write that as, so we can write it in terms of two variables. Often that's how it's written. And so we're going to use the variables n and k here. All right. And it's the value of this function is going to be either 1 or 0. Now it's going to be 1 when n minus k equals 0, or conversely, if you of course just move this k over, n equals k. So when n equals k, or n minus k equals 0, that is when you have the delta Dirac notation at 0, it's going to be 1, and it's going to be 0 elsewhere. So any other integer, and we're going to be talking about this over the integers. So we're going to be talking about them over the integers. And so any other integer number, so basically any other output that's not the Dirac of 0 in the discrete domain is going to be a 0. And then at 0, we're going to have 1. So how do we get 1, or how do we get this to be 0? Well, this n minus k term has to be 0. And so when you just move the k over here, we get n equals to k. So remember this. This is important, and this is the, again, discrete approximation, or this discrete version of the Dirac impulse. So moving onwards, and remembering that, we now have our filter, our signal, and I introduced this formula, or this partial formula, and this is characterizing this at a single point, so at a single n. Now, what is this k, and where does this come from? So what we're basically saying here is, remember, this is an LTI system, so what we're saying here is that we can characterize the signal by multiplying it by a value times the weighted, and we call it weighted because it is this is a coefficient, and it's being multiplied, so it's applying some weight to the delta Dirac function, which is delayed by k. So it's delayed by essentially one sample. So if you want to think about it, the actual formula here we're going to be using is a summation, all right, from k negative infinity to infinity of this value, and that's going to be our characteristic x sub n. So if you want to write down a few values of x, you can sort of see of k rather. So let's let k equal 0. If we let k equals 0, well, we get x of 0 times this delta of n minus k, which is 0, so it's n minus 0, which is just n. K equals 1, we let x1 dn minus k, which is 1. K2, x of 2 times this delta, which is n minus k, which is 2, and so on and so forth. And you can see that it's this coefficient value multiplied by this delta value, which is delayed by one sample. So what we're saying is, a way to think about it is, so this is not the exact notation, but this is just an analogy to think about it. If you have a system that you're trying to observe, so you send a signal or an impulse to it at t equals t1, time 1, then the next time instant, so you send this impulse to it, the next time instant that you want to is t2, and so you're going to be observing the response to t1. So you're going to be sending t1, you're going to be sending this signal, a response at time t1, and then the next time instant t2 you're going to be observing it at, because you can't observe the response. It takes a second to actually get the response, so you can't observe it in real time. It's not a real time. Even if you're observing in real time, as you are, you're getting the data, if you may, in the next time instant. So again, this is just an analogy here. So you're getting you're observing the input of t1 at t2. So you're observing what you sent at t1 at t2 at the next time instant. Now, what does that say? Well, that says that we can we can delay by one sample, right? And that, because we're working in an LTI system where time is invariant, we can delay by a sample, and that allows us to characterize the response of this filter, because it's just going to be or the signal, because it's going to be the same thing, just with a time delay or a sample delay that is constant. That's part of the LTI theory, where it's the same output. The only difference is that it's delayed by some value, in this case k. So we have a sample by one delay. Now, this formula is the characterization of unit impulses. So each one of these deltas is going to be an impulse, and it's the summation, so the multiplication, and then you add them all up, and that's going to characterize the sequence input signal xn. So let's actually just quickly do a quick rough example of that, using some very simple signal that I just make up on the spot. So let xn be a signal, so this should make it clear, and we're just going to make it have four values: 1 at n equals 0, 2 at n equals 2, -1 at n equals 4, and 0 elsewhere. So if n does not equal 0, 2, or 4, it's going to be 0. So this is a very simple signal. A very simple signal. Now let's write this formula again. So let's write this formula again up here. keep in mind that formula. So how do we actually write this signal utilizing this formula? Well, it's quite easy, and I'm going to write it out and explain it as I go. It's very simple. So we're going to start with, of course, our first value of n, which is just 0, happens to be here. So remember, it's 0 elsewhere, right? So this could be a sequence of like 50, but we only care about the values at n equals 0, 2, and 4, because 0, if we just have to add a 0 plus some actual value, say at n equals 2, and then we have n equals 3, which is just going to be 0. So I'm going to just ignore those zeros. I'm not actually going to write those zeros in. So it's 0 elsewhere. So we're really only focused on where this signal has non-zero values. So at n equals 0, what we're going to do is, so we write xn, right, our output is going to be equal to the coefficient, which is just 1 at n equals 0, times the delta of n minus k. Now remember, remember what we set up here. We want this to be 1, because if this was, we want this to be delta of 0, so we get a value of 1. Because if it was anything else, then if this value is anything but 0 in here, then this becomes 0, and then this whole thing goes to 0, and then it's just 0, so it doesn't actually give us our value. So for that to be true, n minus k has to be equal to 0, right? Just by simple, we want n minus k to be 0, and then we just, of course, write n equals k, just by moving the k over. So very simple, right? Not a problem. So n minus k here, and so let n equal k, and n is 0, so k is just going to be n minus 0, so that's just delta of n. Now, at n equals 1, we have a 0, so I'm not going to actually write that like I mentioned. So we're going to write plus. At n equals 2, we have the coefficient 2, right, times delta of n. Now, you'll notice a quick pattern here. So n equals k, right? N equals 2 here. So we have n minus 2, right? Because we have n minus k and n equals k. So we have n minus 2. And so you're going to notice a pattern here. Now, we have a subtract because we have a negative, so it would just be we're still adding, but of course we have that subtraction there. So minus the coefficient 1 times delta of n, again n equals k, so n minus 4. And so you'll notice it's just the delay minus the n value. So it's just the delta n minus the actual n values. So to not prove this actually works really quickly by just plugging in some values. So let's plug in. Let's do the second one. Let's see, is this actually true? Is it actually 2 at n equals 2? Well, let's do x of 2. What is x of 2? Well, what is x of 2? Not a problem. 1 times d of 2, because we're plugging in 2 for n, plus 2 times d of n minus 2, so we have 2 minus 2, right, n is 2, minus 1 d of 2 minus 4. So I plugged in 2 for n. Remember, any value that's not delta of 0 goes to 0. So if it's 0, it goes to 1, otherwise it goes to 0. So this goes to 0 because this is just going to be 0 times something, and so does this. This is a negative 2, so that's also going to go to 0. And we're going to be, now this one, delta 2 minus 2 is going to be 2 times delta 0. And delta 0 is equal to 1. So it's 2 times 1, and that's going to give us 2. Indeed, what we wanted, 2 at n equals 2. Now let's try something that's, let's try one of the values that are not here. So let's try one of the 0 values. So let's do n equals 3. So at n equals 3, it should be 0, as we said elsewhere. So x of 3. Well, plug it into original formula again. 1 times delta of 3 plus 2 times delta of 3 minus 2, again plugging in for n, minus 1 times delta of 3 minus 4. Well, this is a non-zero term. This is delta of 1, which is also 0, and then this is delta of negative 1, which is 0. So again, none of these are delta 0, which means that all of these delta terms go to 0. 0 times anything is 0. So we have 0 plus 0 plus 0, and we get the answer as 0. And so that is correct. So you can see it's 0 elsewhere. And you'll know this will be true for any other value. If you plug in 4, you're going to get negative 1 using the same method. So we've just utilized a simple signal. Now, here's the fun part, and here's where we get to deriving this equation for a filter. What that equation we just used gives us the x of n signal. So now we have basically, by summing all those signal components, right, which are delta functions, we basically have something that looks like this. So going from a prior example, so using our prior example really quickly here, 1 at n equals 0, right? So that's 1. Let's put 1 up there. It's going to be like a straight line like that. 2 at n equals 2. Well, so it's going to be 0 at n equals 1, and then at n equals 2, it's going to be 2. Negative 1 at n equals 4, so n equals 3 is going to be 0, and then 4 is going to be negative 1, and it's going to be 0 elsewhere. And so this is going to be our summed up unit impulse. Sum for x n some signal. Now, because we are talking about the discrete domain, and because we are doing LTI, and now here's where you could get into a lot more theory, and I'm going to try to keep it as simple as I can. It turns out that we can take this unit impulse sum, right, which is a discrete data. If we're inputting this into some discrete signal, call it S, similar to this. So a discrete signal, what's an example of a discrete signal? Well, something like the data that'll be coming out of a digital to your computer to go to a digital to analog converter, right? So an example of discrete data is the data that we'll be using to convert audio from digital to analog, because it's going to be coming as digital discrete data, and so that counts as a type of signal. And so indeed, if we input this unit impulse sum, if we put that into, so bear with me here, if we put that into some signal, we can actually replace this with what's known as H, the impulse response. So let me actually draw it like this. So specifically, our delta component, when put into some signal, discrete signal, yields the same, because we are working in LTI system, it yields what we call the impulse response, delayed by the same k. And this unity between this delta response impulse sum and this impulse response, now that we call it, means that we can rewrite the formula that we had very simply as now y to the n, which is some new output, right? So we're inputting this into a signal, a discrete signal, and now we can rewrite this as the same formula, except instead of the delta, we have h n minus k, where h is the impulse response. Now, this formula here is equal to x of n, right? The signal x of n convolved with h of n, where h of n is the impulse response. Okay, now the convolution equation has a lot of theory behind it as well. We're not going to go into that, but this is equivalent to the convolution in the discrete domain of x of n convolved with h of n. And furthermore, and so what this is saying is, for any LTI system, if we know h of n, the impulse response, we know x of n because that's our signal, that's our input signal that we're getting. So we know x of n. So if we figure out the impulse response, we can characterize any LTI system. This is a powerful theory. This is a powerful theory. So let me summarize that in it's a powerful theory. So we have x of n convolved, so we have this convolution convolved with this impulse response h of n, and I'm going to call it impulse, right? This equals the summation from k to negative infinity to infinity of x of k times h of n minus k. So very similar to that unit impulse. And again, we're working in an LTI system, so this is equal to, and this is the much more common form that we're going to be working with. This is equal to h of k times x n minus k. So how can we do this? How are we able to do this? Well, this is the commutative property, and we're allowed to utilize that group operation. So again, x of n convolved with this impulse h of n is equal to h of n convolved with x of n, which is equal to x of k, so from negative infinity to infinity, of this h n minus k, which is also equivalent to, because of the LTI system, h of k times x n minus k. And so this is often what we're going to be using. The second equation. They're equivalent, but we're going to be using the second one because for any LTI system now, so for any LTI, if we know the impulse response, h of n, for any LTI system, if we know the impulse response, we can completely characterize the signal x of n. This is really important because this is stating the fundamental duality here. It's stating that if we know the impulse response, we can completely characterize it. We can find the frequency response, we can find any response, magnitude response, we can find the phase delay, the group delay, and we can find all these other characteristics just from the impulse response. Furthermore, just like we were looking at earlier, so again, we're doing x of n convolved with this impulse response. H of n is equal to this formula, which is equal to this formula. If we know, so h of n is an impulse response, right? So it's an impulse response. So going to be a discrete impulse response. So an impulse response in the time domain is going to look like a sinc function, and we'll look at that in a second, right? The coefficients of this discrete sinc function, so we're going to quantize this. The coefficients of this are going to be this h of k value, and that's going to be the coefficients of our filter. So at this point, I think it's time to actually go back to the slide that we were looking at, and now we can finally introduce this filter formula with this theory behind it. So right before I do that, I'm just going to bring up this, which is so the third one here we've talked about already, that the processor must finish all the computations in the sampling period. So we'll just skip over that since we know that. But let's look at these two. These are fundamental. We've actually just kind of proven that. The theorem here is that in our FIR filter design, the coefficients, right, the coefficients of the filter are the quantized values of the frequency response of the frequency transfer function h of f. Well, that sounds a little confusing, but really it's not too confusing. If you look at this again, this is our frequency transfer function. In this case, it's h of k. Right? When we take this frequency transfer function and we take the discrete Fourier transform of this, we're going to get this impulse response. Now, we're going to the impulse response, which is infinite in nature, we're going to quantize it just like we quantize a signal like audio, and the coefficients, or the points that we quantize it, the values for those points are going to be the coefficients for our FIR filter. So that's what this is saying here, that the impulse response is the discrete Fourier transform of that frequency transfer function here. And that impulse response that it yields will give us the, we can quantize that, and that will give us the coefficients for FIR filter. Now, number one says something very similar, that the design, the filter frequency response is determined by the impulse response. And that's the duality here. We have the duality because everything in here is actually contained in here. And that makes sense because we're just taking the discrete Fourier transform, right? And we'll look at that in a second here. But the impulse response is the key characteristic, and when we quantize it, or when we take discrete values of this impulse response, that gives us our filter coefficient, and that also gives us our frequency response of the filter. So the way we're going to be doing this, we're going to be doing window design. That's what we're going to be really just focusing on in this video, just as for the example. because that's a very common way to, in audio. And the window design, well, we're going to be using some window function, and it's going to our design is basically going to be taking this impulse response, working backwards, truncating it because we can't go to infinity, and then applying a window function to it, and using the right parameters, we can now take this truncated impulse response, do an inverse discrete Fourier transform, because we're just going the other way, right? We were going from DFT from here to here to get this. We go inverse of that to get this. We can now get the frequency response. We can, once we get the impulse response and quantize it and get our coefficients, that characterizes the entire filter. So these two are basically stating that the filter is characterized by the impulse response, and the impulse response quantized are the coefficients of those are coefficients of our filter, and they're identical, and that shows the duality because we can now take the impulse response, calculate our frequency from it by doing the inverse fast Fourier transform or discrete Fourier transform, and now we're able to actually get the frequency response of our filter. So everything is characterized by this impulse response. So this is why it's very important, and now hopefully that word impulse response has some meaning, more than just a random impulse or a random stretch of energy. So now let us look finally at this formula for the n-tap finite impulse response filter. So it's not going to be too difficult to explain now that we've done a lot of the heavy loading, but this is a general example or generalized diagram of a standard n-tap FIR filter. So you can see that we have an input signal x of n. Each one of these are our coefficients, and these again come from our impulse response. When you see the z to the negative 1, I'm not going to talk about that in detail, as in that is the z transform, which is again similar to the Fourier transform, and it's the z domain, and or the z domain, and we can look at this and just, you can think of it as a delay by one sample, right? So this is very similar to that equation we came up with. Indeed, it's almost the same, and this is a diagram for this equation. So we're showing that we have our input is being multiplied by a coefficient, right? So it's being weighted, and again, our filter, each input point is delayed by one sample. So sort of like last in, first out. And so you can see here that we have, this is a general n-tap, so it's going all the way, to n taps, and we have n minus 1 as our last tap, right, or our first tap if you want to think about it, or first data point, or for lastly delayed data point, and then you have xn minus whatever values in here. So here you have xn minus 0, which is why it's just xn minus 1. Here you have xn minus n minus 2, so when you do the n minus and then you do the parentheses, you're going to get a plus 2, so that's why you have the plus 2, and then same here, n minus 1, and that's why you're going to have plus 1. And for each one you multiply by its coefficient, and then you add them all up and you get your output y of n. That's a general n tap, and so this is each step, each multiplication and addition is called one tap. We call that one tap, and again the formula is very similar. You'll notice it's that formula again we were using again. H of n, the impulse response, times the signal convolved with the signal, is, now the only difference is in the general theory, we were doing negative infinity to positive infinity. While in our filters, we want to keep it casual, which means we want to have our values of x of n, or sorry, our next value be only dependent on prior values, which makes sense in a real-time system. It's not possible to do anything else, right? We can't use future values. So we start our k at 0, and because if our k was negative, so if our k was going -1, well, this xn minus k term would become xn minus some positive k, so it would become xn plus term, which is implying that instead of delaying by a sample or delaying by k, we're now using future values. So we can't use future values in a real-time system. We can only use past values and current values. So that's all we can do. So that's what a casual filter is stating. So this is just all we've done is made it from negative infinity to infinity to now finite values. So now it's starting at 0 to be casual, and it's going to n minus 1 instead of infinity, because we can't go to infinity, but we can go to as high as we want. N minus 1 is the amount of taps, where n is the taps. N minus 1, obviously, because we start counting as humans 1, 2, 3, 4, but computationally we start at 0, so we have to do that N minus 1. It's done all the time in computer science. But so we're going from 0 to N minus 1 taps, and the more taps in general we have, the closer we get to that perfect approximation. However, we require n multiply accumulants for each output. So we require multiply and addition for each of these outputs, right? And gets computationally expensive. And so this is just the same formula again, and it's explaining very much of what I just said, right? So the impulse response here, the quantized coefficients are what h of k is, and then xn minus k is our current input, because each input data point is delayed by 1. So this is the current input, right? And this is actually like our first input, but everything's delayed by 1. And so on the next page, we see this a simple one in action. And again, the filter impulse response determines the coefficients. This is a 9-tap FIR filter, going from so this is again x of n multiplied by a coefficient, and x of n minus 1, again delayed by 1 sample, and then we skip writing all of them, and then we have our last two all the way to n minus 1, which is of course 9 minus 1, which is n minus 8, and then the one right before that, which is n minus 7, and it's multiplied by the coefficient h of 7, and n minus 8 is multiplied by the coefficient h of 8. These coefficients come from the quantized impulse response. So we have our x of n like this. It's a signal, and then it's multiplied by these coefficients here, which are from the impulse response, and that determines this output. So this is the output y of n. In this example, this is a 9-tap filter, right? So you have 9 values, 1, 2, 3, 4, 5, 6, 9, all the way from h of 0 to h of 8. And again, these coefficients are identical to these values. This is a quantized impulse response. From this, we can get our frequency response, and that characterizes the entire filter. So now that we've done that, let's talk about the method that we're going to be using, windowing. So we're going to be using windowing because it's very common audio to actually design a filter. And so the general idea with windowing is, and the next page actually has a better, I think, diagram than this one, this example, but this text-based representative. But the general, I guess, algorithm is you specify a function, so a transfer function. So that is again that low pass filter, right? So that's again our low pass filter. We specify that transfer function, and we expand it. So we take the Fourier series of it, and the Fourier series of that gives you the impulse response. As we mentioned, the duality there, it gives you the impulse response. And the Fourier series, so the Fourier transform and Fourier series, of course, are very related there. The Fourier series is the Fourier transform is a component of the Fourier series. So the Fourier series coefficients, if you look at the formula, right, will give you the quantized values of that impulse response. And that is what we want to use as our filter coefficients. So we're going to truncate the impulse response to our endpoints, which we call our taps, and then we apply our window function to the impulse response to smooth the effects of the truncation. And the downside is we lack precise control, although these window functions are really where we get the power. And so we do lack precise control because we're applying a window function, same as we do with like FFT. When you use a spectrum analyzer, you're using a window function, and you've seen some of these before: rectangular, Hanning, Ham windows, the Blackman windows. I mean, there's tons of them. They're all the same windows for FIR design plus more. And so you'll actually see here that, of course, we lack precise control, but we can get the window functions to be pretty powerful and accurate for our needs. And so we're not designing it from here. We're sort of working backwards, and it's, I think, better described here on the next page, which is a diagram. So pictures worth 1,000 words, and this is again a very good overall example of how we're designing a windowed FIR filter. So we have an ideal low pass, which is what I drew before, which is a rectangular function, right? And that is going to be allowing all frequencies through up to a point. So that's what 1 is. Again, this can be turned to magnitude into decibels, but it's allowing all frequencies up to a cutoff frequency, and then it's ideally just not allowing any other frequency through. This is the frequency domain. In the time domain, these are equivalent. Now, we're actually going to be using, and what everyone uses in the audio and almost any signal processing domain, is the normalized sinc function, which is, get the diagram here. So the normalized sinc function is very similar to the original sinc function, but it just has a multiplied by pi. So it's sine pi x over pi x versus sine x over x instead of sine. So we're going to be using this normalizing function, and what that normalizing function does is, if you look at this very closely, right, when we look at the integers, so let's look at the integers right here, the integer symbol there. Any of the integers are going to be 0 everywhere except for at 0, which is 1, which is going to tend towards 1, right? And so if you look at this, it doesn't look like that straight off the bat, but if you actually take a look really closely here, this is 0, and then this is negative 0.5, this is negative 1, so this is, any of our decimal places don't land on, so any of our integers, all our integers, negative 1, negative 2, so it's going in 0.5 steps there on the x-axis, negative 2.5, negative 3, negative 4, and then we have negative 5 here, negative 6, similarly we have 1, 1.5 again, 2, 3, 4. So all our integers, all our integer values there are 0 on this idealized normalized sinc function, except at 0 it tends towards 1. And so we're using that because it allows us to approximate this function. So this and this are actually equal. When we take the Fourier transform of this this rectangular function, it equals this function. And again, you can look online to see why that's true on the proof of that. I'm not going to go through that here, but if you take the Fourier transform of this, you're going to get that, and vice versa. And so what we're doing here is taking this idealized, these dots saying it going to infinity, right? All those zeros are all going to infinity on both sides. Of course, we can do that, so we truncate it to n taps. Then we have this window function. Now this is just some general window function, and we're putting that window function, we're convolving that window function on top of the impulse response, basically. So we're convolving that, and then we're getting our windowed impulse response. So we're now getting our windowed impulse response, which is our final impulse response. And again, we're working in the discrete domain here, so we're going to be getting discrete values, quantized values here for these impulse response. And from those quantized values, again, we can calculate the coefficients. Now we have all the coefficients for our filter, and again, from here we can take the inverse DFT and calculate the frequency response. And these are side lobes here, which are a result of the imperfection of not perfectly using the infinite sinc function. So we have these side lobes there, and that's really what our windowed design does. Is it gives us a really great steep, very close to rectangular low pass ideal filters, but it gives us these lobes, these side lobes, and you want to make sure those side lobes are not in your frequency cutoff. And so a way to ensure that is interpolation. So we're going to talk about interpolation briefly because it's a very simple topic. Interpolation simply means to and it's done almost basically in every DAC these days. Any high-end DAC has interpolation. Interpolation means we can take our sample signal, right? We can look at this. Now this is a digital signal. It's sampled only 3 times here at sample rate fs. And again, by Nyquist, 1 over the sample rate is our sampling period. We can add some zeros to it, right? So we just pad it with zeros, and now the amount that the times we added zeros is L. So in this case, we did 3 times. So we added 3 in between each sample. So you would have 1 over 3 fs, where L is some integer. And then we run it through an interpolating filter. It turns out this interpolating filter is the same thing in many cases as our FIR filter, and can do it all in one. It's an FIR filter itself. And the interpolator will give you the output, which will now be sampled at L times FFS. So we've now just sampled at L times FFS. We padded this original signal with zeros. Now what does that do? Why do we do that? Well, some of you might recognize right away why we do that. So when we look at our original signal, right? When we look at our original signal, this is how it will look in the frequency domain. Now this is again going to Nyquist theory. So if you need to pause and look at Nyquist theory, go ahead. But Nyquist theory basically states that the signal is band limited and it will repeat itself periodically. And this is a normalized frequency, so it's just showing it's repeating itself at every one repetition. So FFS, 2 FFS, it's repeating itself. And so it's repeating the exact content. And so this is where Nyquist comes into play. Remember, if we don't, if we take, if f of s over 2, right? So this is what we want. We want just this thing over here, right? If we sample by less than f of s times 2 or 2 times f of s, what's going to happen is we're going to have some of this frequency content go overlap into the next spectral image of this, and there's no way we're going to be able to filter that out, because it's going to go through and it's going to come in like this. It's going to overlap, and so that's what Nyquist again states. And now building a filter, so imagine we want that curve, right? We wanted this curve, right? Building this filter here, so if we wanted just this curve and we wanted to cut out all of this stuff because we don't want it, we're just interested in this component, right? 20 to 20 kilohertz, let's just say 20 hertz to 20 kilohertz. Building a filter using this original signal is very difficult because it's a very steep. We don't have much to work with. We can only go up to here, and then we have to cut it off really fast. We have all this spectral content, all these lobes, all these side lobes here coming in, repetitions of this frequency spectrum, and that's again part of the Nyquist theory. Well, this is almost an impossible filter to build, but when we interpolate it by L, now everything gets shifted by L2, so this becomes LF of S, and this becomes 2LF of S. So in this case, if it was, I think, a factor of 3, so this would become 3, and this would become 6, this would become 9, and this would become 12, and now, or what we're interested in is still 20 hertz to 20 kilohertz, for example. So we're still only interested in this, but now all our spectral images get pushed. Everything gets pushed, right? So we have a lot more data, but everything gets pushed over because our signal is now interpolated with padded, and now it's easy to design a filter that filters this out because we have plenty of headroom to work with before we ever get near. And you'll notice that higher quality, higher end DACs generally interpolate quite a bit. And so, look at our typical interpolation implementation. So it's very similar to just a standard FIR filter. Now this is an FIR filter, the same thing as we were looking at earlier. It's just a simplified diagram. Instead of writing the multiplication sign, we just write this little arrow, and that means multiplies. The same as it is an FIR filter, and then it's just saying you're summing at each one, delaying by one sample. This is the general simplified way you'll see it. Now we multiply this, we interpolate. Now we have this clock that's feeding us the interpolation factor. Again, we're going to go over clocks in the next video about DACs, but this clock is feeding us some integer value, so that clock is taking this data in, which is buffered. It's zero padding, so it's adding the zeros and increasing the sample rate. Then we're running this interpolation filter, and it turns out this interpolation filter, this design here, can actually be our filter, our FIR filter, our low pass filter. We can do it all in one. And it just mentions here that the efficient chips will take advantage of the fact that we're adding a bunch of zeros there, so we're going to have some multiply by zeros, and we can then take advantage of that because that's, of course, not a very computationally expensive task, multiplying by 0. And again, these circular buffer and zero overhead looping will be linked down below, but they're efficient sort of exploits, I guess you can call them, of symmetry in mathematics that are used in these transforms and these chips on the hardware level, and that's again general to FIR design. So this is the same as an FIR filter. We're just interpolating it, so we're just adding some upsampling it by a value L. So enough theory, let's look at an example. Right before I do that, though, I'm just going to quickly show you the window functions, some window functions, and you're probably familiar with some of these window functions. Right? And so we're probably familiar with some of these window functions. These are our standard window functions, I call them, because they're very common. Rectangular, Bartlett, Hamming, and Blackman, and many of people have seen these because they're used in FFTs. Indeed, same thing. Same window functions, nothing different. We're using the same formulas. M here is the order, which is going to be generally the size of our filter minus 1. Right, so that's like the size minus 1 of our filter in these windows, on these windows. Right, M is generally our order, so that's what this coefficient M means. And these are just the formulas. You can go online and get the pictures of how these look. Again, rectangular is our simplest window function, which is just like our rectangular low pass filter, which is 1, else is 0, and then we get our other common window functions here. These are all good, but we can get better than these, especially the ones that I told you like in the beginning of the video that sort of draw from, in a way, from IIR filters, and they, to be more specific, they draw from probability distributions, and they sort of have a draw from these infinite sets, so they're more complex windows, but they do a better job than these ones for many cases. So these are sort of our standard windows that we've seen everywhere. So our more complex windows, there's several of them, like the Chevy Chev, the Kaiser, and again, then there's several other ones, but we're going to be actually looking at in the Gaussian window. We're going to be utilizing one that's called the Kaiser window. So really quickly, we're going to look at the Kaiser window, a little bit more theory, and then we can just look at the example. So the Kaiser window, and apologize for the small text, hopefully it's somewhat readable. So the Kaiser window is a little different than the other windows, because in the other windows we look at our order M. So here we look at this, looks like a very complicated graph. Well, it's not that complex. So what this is showing is actually how every filter will look at the end, but the Kaiser window will ask us for some parameters. So what we have here again is just the low pass filter that we were showing in our other video. In our other slide. It's kind of hard to see. I apologize about that, but our response here is this curve here. So this curve here is sort of the one with the ripple here. That's our response, right? And then it goes down and it starts rippling down here. From here to here, right? From here to this line here, this is our cutoff frequency that we want. Now we see the ideal response, which is that rectangular function, but we can't get that ideally, but we go to a cutoff frequency. Let's just call this 20 kilohertz. Now here we have normalized frequency, so it's in terms of radians, and we go from here up to this cutoff frequency. In this case is 0.2 radians, and then we specify so this is what's known as our pass band, what we want to pass in our filter, 100%. We then have a stop band and a stop band attenuation. So how low, and this can be again decibels as well. This is normalized, but this can be in decibels. How low below the fundamental pass band do you want to attenuate the stop band? So our stop band is generally very close to our pass band, and the width between the stop band, the pass band, and the stop band is called our transition width, right? And so in the filter that I'm going to show you in a second that I designed as an example, the transition width is only 2.05 kilohertz, because my pass band is 20 kilohertz, so I want to pass all the frequencies from DC to 20 kilohertz, and then I attenuate very sharply, extremely sharply, and I have a 22.05 so 22.05 as my stop band. And so what that means, I picked that 22.05 because it's half of 44.1, which is what I'm basing that filter off of, 44.1 kilohertz. And so it works out, but you'll see it's only a 2.05 kilohertz width between 20 and 22.05. However, you'll see how sharp of that attenuation it is. So what you to get the Kaiser window, it looks a little complex, but you need to identify a few more things to get the actual window. So what you need to do is first calculate this parameter A, which is the ripple. So the ripple is what acceptable value, normalized or in decibels. So we're going to look at this in decibels generally. What is the decibel of ripple that we want? So within our passband from DC to 20 kilohertz, for example, how much do we want plus or minus deviations in decibels, for example? So we identified that. That's fairly simple, and that gives us a value A. Now, when we have A, we now can calculate M by taking the ceiling function, which is a function looks like stepwise. It gives you the integer value of the ceiling, so you can sort of look that up if you're interested in that. But in general, ceiling function looks sort of like that, right? Depending on where we're going from. And so once we calculate A from our ripple, so we plug in our ripple value, we get A in decibels. Now, whatever our A value is, if A is greater than 21, we utilize this ceiling function and we plug in A here, and that value is M. If A is less than or equal to 21, we plug into this bottom one. So that gives you a value of M. So we have A and M now. Furthermore, we take that A value and we look at it again, and we pick one of these three, not all of them, only one, depending on our value of A. So let's just say our value of A is 30, so it falls below 21 and 50, right? So we're going to plug in A into the second one, and that's going to give you this beta parameter. And the beta parameter is what actually, so the beta and the M are actually what, and especially beta is what you'll be actually modifying to actually give you the the trade-off between how steep or how close this is to the ideal response versus the side lobes and how far they come up and how low their attenuation is. So the side lobes. And there's a trade-off between those two. So again, you calculate B from A, so you get A based on the ripple you want in your passband. Then you get M based on the value of A. You calculate B beta based on the value of A. And then this you'll also need this TW, which is the transition width. Again, that's just from your stop band to your passband. So for example, in this normalized example, it's just from 0.2 to 0.3. So it's just 0.1 is the width. In my example, it's from 20 kilohertz to 2.05, so it's 2.05 kilohertz. There's just the width, the difference between the passband and the stop band. And sampling frequency is just our sampling frequency that we're sampling by, times 2 pi. That gives you this TW, and the only reason you need this transition width value is in this ceiling function. So you'll need it in this ceiling function with A to get your M. So you need a few values here. It looks complex, but it's not really. It's just basic algebra. None of these functions are very complex. I mean, this is just algebra here. Nothing too complex. Now this looks complex here, but it's really not. So the actual window function, Kaiser window function, is defined as a zero order form of the modified Bessel function. So if you think back to calculus, if you remember those infinite series, Well, the modified zero order Bessel function is an infinite series. And you can see it's actually a fairly simple infinite series. It's not very complex at all compared to some of those infinite series that I've seen in my life. It's actually a very simple one. And you can see they just expanded here for 4 terms. And it's, again, has a very characteristic infinite series representation here, going from you see those factorials in the bottom, that are very indicative, and this very classic structure here. This is, again, not very hard to do. You have a computer, but even with hand, this is not terribly hard to do. They'll tell you here that you don't have to calculate I very much because of the denominator. Again, with the characteristic of infinite series, many infinite series, the denominator is going to get very big very fast because of how large these factorials become compared to the numerator, which is much smaller. So you don't have to go calculate too many iterations of this. So the actual window function is this I0, which is that infinite series of this stuff over this. So the bottom is easier to calculate because we have, remember, we have beta. So we, once we calculated, we have the values beta, we have beta, we have m, which are what we want, right? So we plug in beta here, right, into, so let's just say beta was of 5. Well, if beta is 5, we just go ahead and do IO of 5, right? And IO is that modified Bessel function, and so again, we just plug that in. So IO of 5 would be 5 over 2. So we would have to do 5 over 2 because we're plugging in for x, again, to the power of 2i. So it would just be 5 over 2, 5 over 2, 5 over 2 here. Again, we don't have to calculate that many iterations of I, because the denominator gets so big so fast. So again, if beta was 5, we would plug that in for x. We would get 5 over 2 to the power of 2i over I factorial squared, and then we have to now do the infinite series at x equals 5, because that's what our beta was. And again, we don't have to do that many because of how big this denominator becomes. The top looks complex, but it's again just I0 of this stuff. We have beta, so we just multiply beta times the square root of 1 minus 2 n over m. M, again, we have that parameter which we got from up here, and minus 1 squared. So now this just becomes like a normal windowing function. Again, we do the same method. We plug that in into our here. We don't have to do that many iterations because of how big it becomes. But this looks complex, but it's really not if you know your infinite series. This is actually a fairly simple infinite series. This looks, again, complex, but once you get these, it's just algebra and some simple addition here. It's not actually too much complex math. However, the Kaiser window yields us some very nice results. So let us look at this example. So the example I made is in MATLAB, and I made 2 in preparation for the DAC video. And so the reason I made 2 is because, so we're going to be talking about multi-bit DACs and all that in the next video, and the shit audio, for example, multi-bit DACs, they are going to utilize 2 fundamentals. So our fundamental frequencies are frequencies that we allow. So let me just explain that really quickly, very simply. 44.1 and 48 kilohertz are our fundamental frequencies. All right. Now, for in the example, they would have to have 4 filters, right? So we're going to do an interpolator, and we're going to upsample by 8. So we're going to assume, so these 2 filters I did one as a 4 times interpolation, so an upsampling of 4, and that sort of represents a multi-bit DAC, or a DAC that's interpolating, upsampling up to 176.4, because I picked 44.1. Now, for example, the shit audio multi-bit DACs, they have both these as fundamentals, and they go 8 times this for the top tier, and then so for the Gaussian and the Yggdrasil multi-bit, and then the lower the Bitfrost and the New Modi, they interpolate by 4 times. It's very similar. You'll notice it's very similar here. It's just half. It's just half the size too. The filter size is half the size, because it's a cascading filter. So you'll see here that they did it for both 44.1 and 48. So I did it for 44.1. So I just happened to pick 44.1. It doesn't matter. I could have designed 4. So I wanted to do 2 different filters, both for 44.1. One of them is a 4 times interpolator, which is this one. 4 times interpolator, and then this one's an 8 times interpolator. And it's based on the fundamental 44.1, and it's based on 44.1 as our input. And then if you had to 48, again, that would have to be a separate one so it would be 4 filters if you wanted to design 4 times and 8 times. So you'd have to do 2 more filters. But this serves the point. So let's quickly look at, as soon as we look at one of them and understand that one, the second one will be fairly easy to understand. I just want to point out a few differences as we increase the interpolation rate. So let's look at this filter information, right? So this is MATLAB doing a lot of stuff for us. Again, it's a direct form FIR, which means it's a pure FIR filter. Interpolation factor of 4. It's a 553 filter length. So again, it has a length of 553. So that's 553 taps in this filter. That's how many coefficients you're going to have. It's stable in its linear phase type 1, meaning it's even. Some characteristics that I did. Again, we're doing our sampling rate is 4 times the fundamental 44.1, which is 44.1 times 4, which is 176.4. We're designing a low pass filter. It's an interpolator. My ripple, remember, we're using the Kaiser window here, so I wanted my ripple to be just very small, 0.01 decibel, very small. I wanted my passband to be 20 kilohertz. You'll see passband edge 20 kilohertz. And then I wanted my stop band to be 22.05, which is half of 44.1. So that's our stop band. So you can see that the attenuation here is also 100 decibels. So I wanted it to be ideally 100 decibels below the pass band. So quite a steep drop, well down into our noise. So negative 100 decibels again, at our stop band. And you'll see the measurements of this filter are, again, our passband is 20, our 3 dB point, which is our negative 3 dB attenuation, is 20.8. So you'll see how steep this is, right? It's going from 20 to 20.8475, and then our 6 dB is going to 21.025, and then all the way down, we're going to be going down to negative 100 dB essentially. So it's going to be a very steep filter. It goes from negative. So you can see we only have a 2.05 kilohertz as our transition width, right? The difference between 20 and 22.05. Now passband ripple, this is the actual ripple of our filter. You can see how good it is. It's an order of magnitude better than what I asked. It's very, very low, and we'll look at that. And this is the attenuation, the actual attenuation. And again, this just tells you how many multipliers and additives we need in each one. The important number is, again, the filter length, so the total multiplication and addition. So the total filter length, which is 553, but it shows you here. So keep that in mind. 553 is for the 4 times, and again it's based on 44.1, so 4 times 44.1 gives you 176.4. So we're gonna go through some measurements here. First one, let me zoom out here. First one being the magnitude response. So this is our magnitude response. I have it in frequency versus our traditional amplitude, and these lines here show you the passband, which goes from 0 to 20. It's kind of hard to get in one shot, but it goes from 0 to 20, and this is our passband. You can see how flat it is, and then you can see the steep drop. That's going to be, and then these two dotted lines, that's our transition width, and this is our stop band, which is all the way down here at negative 100 decibels as I wanted. And then you see all this stuff, which are all the side lobes, but they are well out of our filter. So our filter is here. You can see how steep it is, and that's why these are called Windowed-sinc filters, or they're also called classic, almost like brick wall filters, because they're so steep. So you see the magnitude response there. Again, I'll zoom in there just to get a better view. See how steep that is, and that's going from 0 from DC to 20 kilohertz, and then you can see it drop down. That's just 22. So this is only 2 kilohertz, but you can see how steep of an attenuation it dropped. This is our phase response, and we have a linear phase, okay, which is a characteristic of casual FIR filters. They have linear phase. That's really important, and that means that the phase changes linearly with respect to the frequency. Now you can see that it's a linear line. It's increasing, right? It's increasing. The phase is increasing as frequency increases, but it's linear. And actually these are also linear. These, even after our so this is all the way from 0 to 20, and it's a linear. These are also linear. They don't look linear, but they are linear. So get the zoom back there. So these are also linear. It just doesn't look like that. They look like sawtooths. The reason they're the sawtooths are because whenever you have negative frequency in those lobes, you have a discontinuity, but it's still linear. It's a linear phase change. So the sawtooth, which is like this, is still linear. When you remove those negative frequencies, well, then you get a straight line. So this is phase delay versus frequency, or phase response. And the next thing is what really want to look at, and that's our impulse response, our classic impulse response, right? Now remember, this is not a so this is not a continuous signal. This is discrete signal. So these are all quantized values, and those each one of these quantized values is a coefficient of our filter. And there's 550, what did I say? 553 was the filter length. So that's how many coefficients there are. And you can see that there's a phase delay. It's about 1.5 milliseconds. You can calculate that from the phase delay and the group delay. That's how many seconds, or milliseconds rather, you'll need for this filter to do a computation, or to do one response. So you can see the impulse response here compared to the normalized sinc function. You can see it's sort of getting there. It's sort of approximating that normalized sinc function. If I zoom into the center, you can sort of see. Now, remember, this is discrete. They just look like they're connected, but there are just 553 samples there in this 3-second span, millisecond span, and so you can see that it's delayed by 1.5 milliseconds. So you can see that these quantized values are our coefficients, and this is our impulse response. This gives us our frequency response that we saw in the magnitude table. Phase delay, again, this is just the delay. This is going to be constant. So this is in radians per hertz. You can see it's 576 radian or 276 radians per hertz, but it's a linear, so it is increasing because 276 radians per hertz. So as the hertz goes up, the phase delay goes up, but again, it's linear, it's constant. You have a constant phase delay, and that's again shown with these types of filters. And the group delay, so the phase delay is the delay of the phase of our sine of our wavelength. So how is our phase delayed? If you take the derivative with respect to frequency of the phase delay, we get the group delay, which is, again, we can show that it'll be the same number, except it's now in samples. So it's a flat term. It's 1 unit order less, so it's just 276 samples, and that's our group delay, and that's how we can calculate how many seconds our filter will take to compute and the delay of our filter. And so our group delay, again, is the derivative of a phase delay with respect to frequency, and it's basically the point, the slope of the tangent line, so at the phase delay. So it's the change in phase delay at a specific frequency point, and again, that number is the same. So it's like taking the derivative of 2x. So if 2x was our hypothetical phase delay, taking the derivative of 2x would be 2, and so the coefficient 2x, so 2 stays the same. So our group delay and our phase delay have the same number. However, instead of radians per hertz here, we're now differentiating with respect to frequency, so now we're just getting samples. So now our group delay is consistent, 276 samples for whatever frequency we want. So that is, again, because of the differentiation. And again, it can be shown that in a type 1 even ordered discrete causal form FIR filter for linear phase, the phase delay and group delay are the same number, the same coefficient. In this case, 276. So this is just an extraneous image. This is just something interesting that I like to show. This is the zoomed in magnitude response of the passband. So this is just from 0 to 20 kilohertz. Remember that ripple I specified of 0.01? Well, you might say, oh, this looks like really bad. Well, look at this magnitude in decibels here for a second here. Look at these numbers and look how close they are to each other. Yeah, this whole thing is less than 0.01 decibels. This is a zoomed in version of the 0 to 20 kilohertz, our passband range. So you can see that the ripple is there, has a very characteristic Windowed-sinc method, where as you get closer and closer to that end of the passband where we have the giant attenuation, we can get more and more ripple. But again, it's well within our 0.01 decibels. I mean, it's even as it is worse, it's an order of magnitude better than 0.01. It's just zoomed in so much, so you can see that ripple. These values are so small. These values are very, 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 very close to each other. I'm just trying to show you that it's there. So there is that ripple in the passband, but it's very small, and definitely within our spec. And it has this characteristic increasing as we get closer. And this is, of course, the end of our passband and beginning of our attenuation. Now, really quickly going to our 8 times interpolator, which is the same exact thing. Take a look at that. I noticed one or two differences. The same exact thing. You'll notice that our fundamental is still 44.1, so 44.1 times 8 gives us 352.8 kilohertz. Remember, the more we upsample, the more taps we have to do. Now, this is going to be, as you'd expect, very simply, it's now 2 times the interpolating rate, right? The first one was 4, now we have 8. The filter length is 1105, or 1105, right? So, well, is that 553 times 2? No, that's 553 times 2 would be 1006. Well, where did that extra 1 go? Well, remember, we have n minus 1 taps, and so one of those zeros, right, because of the way we count, so we only have to add 7 more zeros here, not 8. So we have to only add 7 zeros here, and the other one we only add 4. So we get one of those taps counting, but you can see that is exactly as what we expect. It's 2 times the size, so it needs 2 times the computational power, essentially, and it's a 1105 tap filter, and 1105. Now, looking at some of the data points here, very similar, same stop band, same pass band, same everything. Our passband ripple is just a slight tad better, just because of as we get higher and higher sampling rate, it's going to get a little bit better, just a little tiny bit. I mean, this is very small. Same thing with the 3 dB and 6 dB points. There's just slight differences, slightly more attenuated, so that's good in the case, and just a slight more, like 100.5 versus like 100.2 decibels as our passband attenuation, so just a slight more. I mean, we're currently cutting it with this filter. This is a very, very sharp filter, so in fact, if you like change this 22.05 to something like 20.05, where you just have basically nothing in between the passband and the stop band, you'll actually notice that this taps becomes like 50,000, because it becomes very, very high. Remember, the more taps you have, the closer to infinity, the better you have, better approximation you have of that idealized impulse response. So we're gonna go through these really quickly because it's like the same thing. Now, one thing to note is that the scale of this is just doubled here. So in the old one, this one was 0, 10, 20. Now it's 0, 20, 40. So this is the scale on this one. It's going to look very similar to the other one, but it has 2 times the spectral content, because we're sampling all. Remember, we're sampling up to Nyquist, so that's frequency sample divided by 2. So we're sampling all the way, in this case, to 176.4, or half of 352.8. And the other one, we're going to be sampling to only half of 176.4, because that was our frequency sample. Now, if I made this scale the same as the other one, where it went in 0, 10, 20, 30, you would see this expanded and have double the content. But you can actually sort of see that it has double the content because of how dense, how dark these lobes are. So there's 2 times the content, spectral content in there. And indeed, you can see how, just like we talked about earlier, that filter, remember, we still are only interested in the same 20 kilohertz from DCs. You can see now we have all this extra room to work with, and that's why higher up sampling in this case works better, albeit at the cost of computation. So you need to make sure that your computer can handle the computation, your DSP chip can handle the computation. If your DSP chip can handle the computation, then this interpolator is a good way to go. The higher interpolation rate, the better. But remember, it comes at the cost of higher delay. And so you can see here, this is much, it was out here in the other filter. Now it's much closer, so we have all this extra room to work with. However, this filter, no problem. Again, very sharp cutoff. This is 0 to 20. So the same stuff. Again, we have our linear phase. It's going to look very similar. Phase response, again, is very linear. It's a linear line with respect to the magnitude here. It's increasing. It's increasing. And then it's still linear. It's just the sawtooth, but it's a linear, so it's just a constant phase delay. So that's okay. Now look at this impulse response. Look at how much better it looks compared to the other one. It looks a lot more idealized to the idealized sinc function, and that is what the benefit of this interpolation is. Again, we get the higher, unfortunately higher computational rate, twice as much, but if you're able to handle that, if your DSP chips are powerful, if your algorithms are well designed, well, now look at this. Remember, it's discrete. There's 1,105 coefficients of this impulse response, or 1,105 data points in between this 1.5, this 3 millisecond steps. That's why it looks like they're connected, but they're not. They're just so close to each other. And we can see that it's looking more and more like a idealized sinc, normalized sinc function, and that's what we want. As we increase the taps, we get better and better response, closer to that sinc function. So our phase delay is going to be 2 times as we'd expect. The interpolation rate went up by 2, while our phase delay is again linear. It just went from 200 and I believe 26 to 200, 552. Yeah, so it just doubled, which is exactly what it's supposed to do. So it's doubling. So our phase delay is doubling. So that's again the downside, because now we have a longer phase delay. And again, taking the derivative of that phase delay with respect to frequency gets rid of that. Remember, this is increasing because it's 500. It's constant, but it's radians per hertz. So as the hertz increase on our x-axis, we have our increasing phase delay, which is why we have that negative line when we looked at our phase response, and it was increasing right as the frequency increased, but it was linearly increasing, and it was getting more and more negative, which is what we'd expect. Again, that's characteristic of this type of response, of this type of filter. Differentiate this with respect to frequency, get rid of that hertz component, and we have a group delay in samples, which is going to be the same as the phase delay in terms of the number. Apologize about the zooming here, but that's 576. So sorry, 552 group delay. So that's our group delay. Again, that's a consequence of interpolating by that much. But if you can handle it with your filter and computational power, well, then it's good because of that impulse response, and the closer we get to the idealized one. So it's a trade-off, but that's why you'll see many of these upsampling to this high of a rate. You can see that this is again 2 times what the last filter was, the 4 times. It's just the same, and it's the derivative, and the group delay is 552 samples for any given frequency in our filter. And then the last one is just the same zoomed in passband. This one is again just the same, 0 to 20. Again, very close. It's, if you look at these numbers again, it looks like it's a lot, but it's not. These numbers are extremely close to each other. Very similar to the other one. I mean, maybe it's just a tad better ripple response, but just about the same within the spec that I asked of 0.01. So this just has double the computational power, essentially, of 1,105, which is n minus 1. So it's just 2 times minus 1, 2n minus 1, which is the formula that you would use for this interpolation. So if you went to, for some reason, if you went to 16, which no one really does, but if you went to 16, well, now you'd be multiplying by a factor of 2, so now you, but what happens then is then your filters then tend to become unstable because you can't get that ideal from every window function, and you can't get that much of a of a brick wall, so you can only get so ideal before you start getting really messy. And if you play around with this, if you just change these numbers around, or if you even just specify like an order of like 5,000, and you look at some of the responses, you'll see they look very, very off because the filter can't actually reasonably do it. It's not mathematically possible with this window filter. You can see this is a very good good basic window. Yes, it's computationally expensive with 1005 at 8 times interpolating, and 553 at 4 times interpolating, but it's a good filter. So if you can handle it, it has all the right characteristics that you should have in a nice FIR filter. And just to verify, to close out, using the spectrum analyzer in MATLAB here. So actually, for this one first, so we have, this is a spectrum analyzer. What I've done is I fed it some random Gaussian white noise, which is just some white noise. So all the it's probability distribution Gaussian white noise that adds up to 1. So the sum of all the frequencies, the components add up to 1. So it's just randomized white noise, Gaussian additive white noise. And you can see I applied that to my filter, and then I ran a spectrum analyzer on it. So I ran like an FFT on it, essentially, and you can see our filter response. Well, there's our passband. You can see our drop, and you can see I have these 2 marks here going from, so this dotted line is at my 20 kilohertz where I wanted my passband to end. You can see the magnitude response is quite good. You can see that it drops to our so you can see that it's very steep. Now this one is, by the way, for I only did it for the ran this for the 8 times interpolator for the 350 so for the 350 2.8 kilohertz ones for the 8 time interpolator. I only ran it for that one because it's not to be repetitive again. So again, this is just showing the filter response is exactly how we would like it. You see how steep it is from our 20 kilohertz passband. You can see it's nice and flat here, Gaussian white noise. This is exactly how it's supposed to look. The next image we have, I just moved it, the cursor point down to my stop band attenuation frequency, which I wanted at 22.05, and you can see that a measurement here. So we can see at 0 hertz we have power of 4 dBm, and at 22.05 you can see negative 60 dBm from fundamental. So quite a bit. Now, it's not, because this is an FFT, it's not going to give us exactly the perfect filter response. Remember, I put 100 dB in there on my filter design, but this is the magnitude response in real life with the real spectrum, with the real randomized white noise and spectrum analyzed. But it's still perfectly adequate. I mean, 60 dBm is negative 60 dBm is quite a bit, and that's still 22. So that's just 2 kilohertz more. You'll notice that in just to demonstrate in the last image here, I moved this to a random point. I moved it to 28, which is just a little bit more than 22. So just moved it over a little bit just to demonstrate. Now we're well into the negative 100 dBm range. So you can see this is 20, again 20, This is about 22.05, right around the 60 range. And then you can see how steep it drops. This is like 28. So it's a very steep filter. And then this is all our repetitive lobes. And you can see that they're well down into the negative 130 dBm range. So you can see this is a very steep brick wall filter that is ideal of a characteristic FIR filter. And you can see that this spectrum analyzer is again just the MATLAB one, but it's just verifying that our filter does work when applied with some randomized white noise. You can try it with pink noise as well as whatever type of data you want. I just chose white noise, but I also did it with pink noise, and you'll get a very similar result. So again, this is just to confirm the filter is working as planned. So if you were designing a real filter, of course you'd want to run it through a spectrum analyzer and get data points. Ideally a real spectrum analyzer, not just the MATLAB one. Real in quotes, of course, just a spectrum analyzer. But this will suffice again for the theory and example, because I'm not actually designing a filter here. I'm just designing a filter for example, but not for actual sale. So to conclude, I just have this picture here of the zoomed in Gaussian white noise to the passband. It's just a zoomed in version of that spectrum analyzer content. Again, all of those were for the 8-time interpolator, and you can see, well, it looks exactly how it should. It's just a randomized Gaussian white noise that adds up to 1 as a probability distribution. On the top here, you can get, of course, these images for all your window functions in general, like your rectangular, your Hamming, your hand, all those ones I showed you. But just wanted to show you the Kaiser one that we've used with an alpha of 3 here, and so you can see it here in our time domain here. We have our samples, right? And you can see at alpha 3 we have a response like this for amplitude. This is a time domain, and then our frequency domain we have this very sharp one. So you can see here, as we increase our alpha, so alpha from 2 to alpha to 3, in general what we get is much better attenuation, because look, we have attenuation of only negative 60, negative 70 decibels here. Now over here we have negative 90 to negative 100. We have much better side lobe attenuation at the downside of losing the sharpness of our passband. So our passband here is now more wide and it's not as steep. And so again, this is a Fourier transform window function, the Kaiser window with alpha 3 and 2, just to show you two different examples of the Kaiser window with different parameters rather, and the trade-offs you get. So you get better. So in this case it's generally fine because it's such a steep filter, but like I said, you can't keep on doing this forever. Like, you can't keep on increasing the order, otherwise this filter will become unstable, unlinear, and lose its LTI properties, and then well, then the filter is kind of useless, and you can basically not have a workable filter. So nothing is perfect, but again, this is a good approximation. So so this was just an example filter that I used with a Kaiser window, which is not very commonly used in theory, but well, it is commonly used, but it's not common, as in it's more complex of a window, so I wanted to show it. And the last thing I have is, just in case anyone's curious, this is just that phase shift and phase group delay and phase delay. And you can see, so the phase shift is calculated as this. So this is the definition of our phase shift, right? and it's the arg function, and this function here is representative of the in the complex frequency range, and you can see that because we're working with omega I, which is of course a complex frequency, and the this function will return the angle, the positive angle that represents the point from the origin to the point to a point um, on the complex frequency range. So you could read about that function online if you want, but this is the definition of the phase delay. And so we're working in the complex frequency domain because that's what the frequency domain is. But what I really wanted to show was, of course, just this down here. This down here is our phase delay. You can see there's a negative sign because remember it was like decreasing like this, right? It was linear, but it was increasing more and more negatively. So that's why we have a negative. And so it's just the negative phase shift over the frequency. So that's normalized. That's how we got radians per hertz, right? And then if you take the derivative of that with respect to the frequency, we get the group delay. And so you can see how this is very simple right here. You can see how the coefficient would be the same in the type of filter we design. Because of all you're doing is taking this derivative with respect to frequency, so you're just getting rid of that per hertz part, and now you're having it in samples or in times. That's why it's called a group delay. So it's the integral. It's the derivative. So it's the slope of the tangent line off the phase delay. So it's the point at the phase delay, and that is the derivative. And so that's how it can be calculated in general, even if it's not the same as. So it doesn't have to be the same as the phase delay, the group delay, but it generally is. But these formulas stand no matter what. So I guess it's just a snippet from Wikipedia for those of you too lazy to read through the entire article on phase and group delay. I'll again leave all of this information in the description of this video, and for those of you who have stayed through the whole thing, appreciate it quite a bit. Hopefully you learned about digital filtering, and hopefully you learned again the benefits of our digital filters, how we do our digital filters, our interpolating mechanisms. We saw the difference between the 4 and the 8 times interpolation. We did that very important duality, which I think is the most important lesson from this whole thing, the duality between the time and the frequency domain. So if you really understood that with the delta function and the shifting and the convolution principle and how we got those, drive that equation, well, then you're in a really good position. And if you understand how the impulse response completely characterizes an LTI, linear time invariant system, then again you're in a great place. Because the next video I'm going to probably reference like some topics from here. I assume that the understanding is there from this video. Hopefully it's not too complex, but yeah. So the next video will be about digital to analog converters, and that will be probably talking about the standard digital analog converters like R2R, binary weighted, thermometer weighted, all our DAC structures. We'll really get into the DAC structures and how a DAC works. Now that we got filtering out of the way, it's going to be a lot easier because filtering is ideal. I think it's a little bit harder even than to describe than just the DAC itself. So we'll go through the structure of the DAC. We'll read through the analog devices data sheets for the really high-end DACs that that are in the, for example, the multi-bit shit, audio, DACs, and we'll look through how they're constructed. They're constructed in a very unique, patented way, but of course, the block diagram is there, so we can look through that, and we'll talk about DAX, and then it might be a third video if I can't get it in the second one, which will be a complete characterization of delta sigma DAX, because delta sigma DAX operate in their own unique way. Might require a separate video for that, so that might make this a three-part series. Appreciate taking the time. If you like this video, found it useful, please share, like, subscribe, all that good stuff. If you have any comments, questions, leave them in the comment section below. I'm happy to answer questions, and hopefully you learned a bit from this. Again, I tried to keep the theory and the complexity at a minimum, but also at a required level to understand fully. So we didn't do a full derivation of like the Fourier transform and everything. We didn't do full derivations of all the formulas, but I think we did a pretty good derivation of how we got our FIR formula. And if you understood that and understood the basics of the design and the theory to the example, and then verifying everything, and just understood the benefits, and if you look through some of the links I have in the description, you'll definitely have a good understanding of digital filters. So until next time, with part 2, DAX, now we'll continue onwards, and I'll see you in part 2. Thank you for watching.